It's a pleasure to introduce Professor Ved Datar. He will speak on the topic which is entitled On Yau's Uniformization Conjecture, Part 3. Please go ahead.
Thanks to the organizers for the invitation and for letting us give this sort of three-part lectures so that we could sort of describe, indulge ourselves and describe a lot of details of our work. So this is the third and the final part. Right. So I'll basically talk about some work that's in preparation where we improve the theorem that Vamsi and Harish mentioned. Namely, we can now prove the following theorem. Let X omega be a complete non-compact Kähler surface. So dimension X is 2 again with positive sectional curvature, then X is biholomorphic to C2. So this is really the sort of full weak version of Yau's conjecture without any other additional assumption. So in particular, we can do away with the sectional curvature upper bound in our previous work. All right, so let me make a few remarks. So as Harish mentioned, by this very famous result of Gromol and Meyer, the positive sectional curvature already implies that the manifold is diffeomorphic to R4. And then by a theorem of C.P. Ramanujam, it turns out that in order to show that X is biholomorphic to C2, it's actually enough to prove that X is quasi-projective, right? So again, I mean, this might start sounding like our party line, but let me just reiterate that we're making no geometric assumption at infinity, and this seems to be sort of the first such result. Uh, so the general strategy is usually to construct maps into projective space using sections of some line bundle or holomorphic functions, but you can just think of holomorphic functions as sort of sections of the trivial line bundle. And for technical reasons, these sections need to form an algebra. And non-compactness is a major issue. So one needs many finiteness results, right? And there are essentially various versions of what mock estimates. Vamsi already referred to one such estimate in our previous work. So essentially, the key point, even in this new work, is to obtain sufficiently good Bezout estimates. So let me just give you a quick example of the Chen-Zhu theorem that Vamsi talked about and that we use in our previous work. So the point in Chen and Zhu is that they use L2 integrable sections anticanonical of pause of the anticanonical bundle. So then when you assume that the sectional curvature is bounded above, this actually implies that these sections will all be bounded via mean value inequality, and hence they actually form an algebra. Now, in general, of course, if you multiply sort of LP functions, LQ functions together, or multiply L2 functions together, they need not give an L2 function. So it's not clear if you just use L2 functions whether you get an algebra or not. Right. So the first matter that we had to take care of was to define the right kind of or to consider the right kind of function spaces. So again, let me remind you of this main sort of PD result that we obtained in our first paper. This says that there exists a PSH function phi on X, which is Lipschitz and satisfies this finite Monchampère condition. Right. So for now, simplicity, just pretend that phi is smooth. In the actual proofs, I'll maybe make a few remarks right at the end on what one needs to do. I mean, extra, since we are just dealing with a Lipschitz function. So this is essentially, and Vamsi has already talked a little bit about this. So for now, just pretend that phi is. We consider the trivial line bundle with the Hermitian metric e to the minus phi and consider tensor powers of L with the corresponding metrics e to the minus q phi. And we denote by gamma pq phi the space of essentially LP integrable functions with respect to the weight q times phi. Okay, so notice that the elements of the space are really holomorphic functions because L and hence L to the Q is really the trivial line bundle, but the bundle viewpoint is actually much more convenient for us. So I'm going to stick to that. Also, by the Hurmander L2 method, since the Ricci curvature is positive, one can actually show that by choosing Q large enough, this space is actually non-empty. So we are actually dealing with non-empty spaces, right? Okay, so then we put RQ to be you consider these gamma 2 by k spaces. So let P be of the form 2 by k, where k is some integer and you some natural number, and you essentially take the vector space spanned by all such elements, and then take R to be the direct sum of all these RQs. So an elementary, application of Holder inequality shows that we actually do have a graded algebra structure. And now let M be the corresponding function field. So that just means that you take two elements in the same RQ for the same degree Q and you divide them. You consider this particular fraction field where you only are allowed to divide sections of the same degree, so to speak. So why does one do that? This is kind of standard because morally speaking, if we embed X into Pn using sections of R, then M would be like the field of rational functions on X. So just as an example, if you take the complex projective space, then the rational functions are of course given by quotients of homogeneous polynomials of the same degree, right? So that is why one considers a field of this sort. A key point, which is really the reason why we have to work much harder, is that in our case, phi does not necessarily have a lower bound. So of course, if one improves our PD result and shows that phi has a lower bound, then uh, everything that I'm going to talk about will become much easier, right? But unfortunately, we cannot prove a lower bound as of now, and because of that, we do not have a containment of this sort. Now, I must say that this idea of using LP integrable functions goes back to an old paper of Demai in the mid 1980s, uh, where Demai actually, you have heard about all these sort of papers which assume some geometric hypothesis, maybe something about the asymptotic geometry and so on, and concludes that, M is biholomorphic to C2 or Cn or and so on, right? But Demai had this very beautiful paper in the mid 1980s, which was more or less a complex analysis paper in the sense that uh, he proved quasi-projectivity or proved I think even a manifold being affine. So he essentially characterized quasi-projective manifolds using purely complex analytic data, right? So he said that if you have complex analytic data and some topological data, so if he said that if you have a weight function that satisfies certain nice properties, including sort of finite Monchampere mass and so on, then you have quasi-projectivity as long as you know something about the topology, right? But the big sort of advantage in his case was that he actually, in his case, these LP spaces had these containments, which we do not have because we do not have this lower bound, right? So life is much harder for us. Right, but I should still say that the main motivation for using these LP spaces goes back to Demai's work. So the first key step in proving any sort of quasi-projectivity is to obtain some sort of finite generation result. So let me maybe state and sort of give an outline of a proof of an actual proposition, because later on everything is just going to be an outline and I'm not actually going to say much about the proofs. But our main finite generation result says the following, that firstly, we can show that these RQs that show up are actually finite dimensional, and this function field is actually finitely generated. And in fact, we can show that there exist sections S0 to S3 in RQ for some large value of Q, such that M is actually generated by polynomials in these variables. So the general proof strategy follows some old arguments of which are called sort of Poincaré-Siegel argument, and this was essentially brought to bear on such problems by Mock in several of his papers that Vamsi and Harish have already alluded to. So it turns out that it's actually enough to, again, this is due to Mock, it turns out that it's actually enough to obtain an order estimate. So if you take a section S in RQ and you fix a point O, you would like to show that the order of vanishing of this section at that point O is bounded above by something that's linear in Q. Okay. In turn, again, by a trick of Mock's, Mock noticed that in order to prove such an order estimate, it's actually enough to obtain a bound for an integral of this sort. Okay, so notice that this is very similar to the integral that Vamsi talked about en route to proof that the Ricci squared is bounded. So these sort of estimates are called Bezo estimates, and in fact, this will be a very special case of our Bezo estimates. Okay. All right, so now let me maybe give you a brief outline of the proof of our theorem, and then I'll return to the main technical part, which is namely the Bezo estimates. Okay, so the idea is once you have finite generation, you can just consider this map F naught given by these sections that show up in the finite generation proposition. And the point is that this will actually be defined and an injective immersion outside of an analytic set given by the vanishing of this explicit form. Okay, so then one can show that additionally, that if you look at the image of this U naught, then that is actually Zariski open in a projective surface using an old characterization due to Simha. Okay, so Simha's characterization basically works this way, that one has to show that if you take any hyperplane in P3, then that intersects the complement of F naught of U naught in Z at finitely many points. So if for each hyperplane it intersects the complement in finitely many points, the complement has to be an algebraic set. Okay, so again, this involves trying to estimate some intersection numbers. And so again, this involves Bezo estimates. So this will again be a consequence of our Bezo estimates. So this is quite nice because we almost have everything that we need, except this map is only a biholomorphism away from this analytic set, right? So one needs a way to extend this across this analytic set. Okay, so also notice that our hyperplanes are actually hyperplanes in P3 are given by linear combinations of these variables. So they're actually linear functions in S0 to S3, right? So in other words, they'll also be elements of our function spaces. So we can apply our Bezo estimates. Okay. Right. So now, in order to extend this across this analytic set, we firstly notice that by a topological argument from this paper of Demai that I've already referred to, it turns out that V naught has actually finitely many irreducible components, and by an elementary argument, one can argue that that these cannot have isolated points. So they're basically a finite collection of curves, right? So all the irreducible components of V naught are essentially just a finite union of some curves. So now the idea is that you pick smooth points on each of these curves. Then one can actually choose by Hurmander's L2 method, one can actually choose sections in some RB for some B large, such that these actually form coordinates near each of these xi's. And then you repeat the same argument from the previous slide. So by doing so, we get a map F1 now, defined on some complement of some analytic set V1, so call that U1, you get this map that has all the properties from before. And so again, now the key point is that this I should have said the V naught that I had from the previous slide and this V1, they will actually also intersect in a finite set. And again, this is computing intersection numbers. So this goes back to, again, our Bezo estimates. Okay. So then by finally choosing Q large enough, one can actually then show that if you take the Kodaira map given by a basis of sections for RQ, remember part of our finite generation theorem was that RQs are finite dimensional. So you take for Q large enough, you take a basis of sections for RQ and look at the Kodaira map. It turns out this is well defined and an immersion everywhere. And then one proves that phi is injective. So this actually requires a little bit of an argument, and uh, uh, so we this is the place where we couldn't really understand a piece of argument in Mock's paper, and so we had to sort of argue a little bit differently. So the idea is that one has to sort of lift everything to the normalization of the projective surface containing phi of x, and then Mock's argument actually works for once you lift everything to the normalization. And then finally, we have to again show that phi of x is Zariski open in a projective surface. So we once again run the Simha argument. Okay, so here there's a slight technicality because again, to run the Simha argument, we have to show that if you sort of intersect this phi of x, once you lift it to the normalization, will be contained in a projective surface. So then one has to show that hyperplanes in that ambient projective space will also intersect the complement of phi of x in that projective surface in finitely many points. For that, we need to know that once you lift everything to the normalization, these hyperplanes are essentially again given by things involving sections from our spaces RQ, so that one could again appeal to our Bezo estimates. So this requires a little lemma in algebraic geometry, which again we actually asked ChatGPT to give us a proof, and I think, I mean, that seems standard, but it's just that we are not experts in algebraic geometry, so for us. We got that from ChatGPT, but it seems like it should be probably well known to sort of experts in algebraic geometry. All right, so maybe in the last 10 minutes, let me say a few words about the Bezo estimates, because really this is the technical heart of our paper. So let V1 and V2 be two positive Lipschitz continuous functions satisfying estimates of this sort. So it's a bit technical, but uh, I just want you to notice that on the right-hand side, you have involving the sections in RQ, you have terms involving some derivative, one derivative of the sections in RQ, the strange term SI tilde, and it also involves sections of the canonical bundle. Okay, so this strange little SI with a little tilde is basically essentially, I mean, it's a technical thing that we need to introduce in order to be able to prove our Bezo estimates. And this is really because in our case, we are actually taking, if you recall the definition of RQ, RQ was defined to be the sum of LP integrable functions where the P might vary from section to section. So in general, an element of RQ will be of the form summation Ti, where summation Tj, where each Tj belongs to some Pj integrable space, right? So then this tilde is basically just a product of these TIs. So again, this is just a technical thing in order to make the Bezo estimates work. Okay. But happily, even if, I mean, ideally one would actually not want any term of this sort. But happily, even if we have such a term, we are still able to use our Bezo estimates, right? And in order to prove the Bezo estimates, it seems like one would need a term of this sort. Okay. Right. So suppose further that the zeta i's are satisfy, I mean, the dd bars of vi's satisfy some positivity condition. Namely, if you define zeta I to be dd bar of vi plus beta I times dd bar of phi, then that's non-negative for some positive beta I. Then our Bezo estimate says that if you take the integral of zeta 1 wedge zeta 2, that will be uniformly bounded by a constant independent of V1, V2. And the only dependence will actually be on this positivity, beta I. right? This constant which is needed in order to make zeta I positive. So the only dependency on Vi comes via this positivity. And this is really crucial to all our applications, including in the finite generation result. So these are extremely, I mean, if you think about it, they're extremely sort of flexible estimates, because firstly, I mean, we only assume something on the upper bound of Vi. Uh, and the only dependency on Vi enters via this sort of positivity. Okay. And of course, the right hand side is bounded because our weight phi has finite Monge-Ampere mass. So I should also mention that we actually also need a version on the projectivized tangent bundle of these Bezier estimates. And again, this is because when one applies the Simha criteria, one needs to, by an idea that again goes back, like many of our techniques, it goes back to Mach, that in order to apply Simha's criteria, one needs to control some Gauss-Bonnet integrals of curves. And for this, Mach had a very clever idea of proving some Bezier estimates on the projectivized tangent bundle, and those can be used to control some Gauss-Bonnet integrals on curves that are given by vanishing of sections in R cube. Okay, so we also need a version of our Bezier estimates on the projectivized tangent bundle. Okay, so let me make a few remarks on the proof of the Bezier estimate. So the proof involves a delicate integration by parts. As Vamsi has explained, one needs to smoothen out phi and also use the Bedford-Taylor theory. But we cannot directly work with the smoothened out potentials since the finite Monge-Ampere part is lost. Right, so then we also need to use sort of L2 estimates on S and on the gradient of S, but no more derivatives on S. So when one tries to use integration by parts in higher dimensions, it turns out that one would have to sort of control more derivatives of S. And this is the main reason why our methods, even the analytic part, these geometric estimates, for us, we have to restrict attention to n equals 2. We actually, this Ricci squared result that Vamsi mentioned, we actually can also extend that to more or less, or we have more or less an idea that this could be extended to also n equals 3. But beyond that, right now, I think it seems impossible to do that, because one would have to sort of put more derivatives on S, and we don't know how to control those. So a key point in our approach is that if you take a section in these function spaces, then those the norms of those sections are actually a polynomial growth. Okay. So in fact, there's a beautiful result of Gangliu that if you take a non-trivial holomorphic functions on an X, which let's say has positive bisectional curvature, then in fact they cannot be of polynomial growth unless X has maximal volume growth. Okay, so that means these weights Q phi really do matter, because without the weights, one wouldn't actually get polynomial growth sections or polynomial growth holomorphic functions, unless one is working with a maximal volume growth uh, surface. And under maximal volume growth, as Harish has already mentioned, the Yau's conjecture is already known, right? So we are actually, in our work, we have to deal with possibly non-maximal volume growth manifolds, and so then there are no non-trivial holomorphic functions of polynomial growth. So unless you actually measure their unless you measure the size of those holomorphic functions using a weight. So these weights really do matter. Okay. So, and then as Vamsi explained, to prove, even to prove, for instance, this polynomial growth, we basically use the heat flow for time t equals 1 and work with psi. So the advantage of working with psi is that dd bar psi has an upper bound. And so then one can actually use the Bochner formula to conclude the polynomial growth with respect to the weight q times psi. But then to go back to phi, because notice that that's by this ChatGPT lemma that Vamsi talked about. Psi is less than equal to phi, essentially. So the Hermitian metric of phi is actually smaller than the Hermitian metric of psi. And yeah, the proof is much more technical owing to the fact that we have to take the sums of things that might lie in different LP spaces. So the proof is much more technical of these Bezo estimates. Okay, so maybe I'll end with sort of speculating a little bit. So let X omega be a complete non-compact Kähler manifold with positive bisectional curvature. So I'm now thinking about the original strong form of Yau's conjecture. So a natural thing to do is to try to sort of divide Yau's conjecture into three steps. First, show that X is strongly Stein. So by this I mean that you not only show that it's Stein, but you actually show that there's a PSH exhaustion function with a uniformly bounded gradient. Why? Because then our PD method will actually be applicable. Because our PD method works in all dimensions. So then one would actually have a Lipschitz weight with finite Mochampere mass. If one can show that that a Kähler manifold with positive bisectional curvature is also strongly Stein. So that would be the first step. The second step, I mean, Stein already gives you that your X lies as an analytic subset of some large Cn. The next step would be to actually show that this containment is algebraic, or to show that X is quasi-projective or affine, right? So there, I think one would like to sort of generalize our Bezo estimates. So if one can extend our Bezo estimates, then uh, then it's quite likely that one can actually show quasi-projectivity or affineness, depending on what your perspective is. But of course, as I explained in our case, because we are using integration by parts, right now we don't know how to extend this beyond n equals 2. And then finally, of course, one would need a Ramanujan type result. So the obvious generalization of Ramanujam's result in higher dimensions is false. So if you take, there are apparently contractible threefolds even with which are simply connected at infinity. Affine contractible threefolds that are simply connected at infinity, but they're not C3, right? So one would like a Ramanujam type result, assuming that the bisectional curvature is positive, say. Right, but that's, I mean, that seems to be completely out of bounds right now, out of reach right now. Okay, so let me also end with this rather intriguing question. So we are very surprised when we started working on this problem that apparently it's not even known whether this very simple sort of complex manifold C cross C star, whether that has a complete metric with positive bisectional curvature. So even this very simple example seems to be open. So this should tell you how sort of far-reaching Yau's conjecture is and how little is really known about it if you don't assume anything extra about the geometry at infinity. So maybe this is a good place to stop. Thank you for your attention.